Buenos días con todos los presentes. Estamos a punto de iniciar la presentación del ingeniero Diego Marchetti en el primer Congreso Internacional de Ingeniería Geotécnica de GeoUPC. Voy a presentar el slide. Good afternoon, Engineer Marchetti. I'm about to show our slides of the presentation itself, and then you can start doing it after the presentation, right?
Yes. Sorry, can you repeat that? I didn't hear it.
Okay. I'm about to show the presentation, the slide of GeoUPC, just to make the introducing, and then you can start sharing the slides after I finish.
Very clear. Great. Thanks.
Thank you. Okay. Chicos, como mencioné, este es el primer Congreso Internacional de Ingeniería Geotécnica. Welcome again, engineer. Thank you for your participation on here. This is the second one of the day.
Shirley, no te preocupes, yo me puedo encargar de presentar esa parte.
Sí.
Ok. Good morning a todos los presentes. Good morning, Engineer Marchetti. Vamos a presentar la estructuración para el día de hoy. Primeramente vamos a conocer un poco más al equipo GeoUPC. Vamos a conocerlo al ponente, ingeniero Diego Marchetti. Vamos a ver su tema de exposición, que es el Marchetti Flat Dilatometer and Seismic Dilatometer Sdmt for In-Situ Testing. Y al final de la sesión habrá una ronda de preguntas del público asistente que pueden ir formulándolas desde ya si quieren hacerlo o han investigado el tema. Siguiente diapositiva, por favor, ingeniera Shirley. Ok. Nosotros somos el equipo GeoUPC. ¿Pero qué es GeoUPC? Somos un equipo conformado por alumnos de la carrera de Ingeniería Civil de la Universidad Peruana de Ciencias Aplicadas, UPC, y tenemos como razón de ser nuestra formación como profesionales en el ámbito de la geotecnia. Nosotros conformamos un espacio crítico y de investigación donde participamos y creamos actividades para la comunidad estudiantil con el objetivo de promover y fomentar nuestro desarrollo personal, profesional y llevar todo lo aprendido de manera teórica a la práctica. Siguiente diapositiva, por favor. El tema de hoy día va a ser un tema libre, es el tópico. El tema a tratarse va a ser Marchetti Flat Dilatometer and Seismic Dilatometer Sdmt for In-Situ Testing por el ingeniero Diego Marchetti. Es un ingeniero titulado en Ciencias de la Computación de la Universidad de Pavia, Italia. El ingeniero Diego Marchetti trabaja desde 2001 en asociaciones con el profesor Silvano Marchetti, creador del dilatómetro Marchetti, DMT, en 1980. Utilizado en más de 80 países del mundo. Juntos desarrollaron y patentaron el dilatómetro sísmico, Sdmt, en 2004, y el dilatómetro automatizado Medusa DMT, terminado en 2019 y empleado hoy en día en 4 continentes. En 2009 fundaron el estudio Prof. Marchetti, empresa que consiste en el diseño, la producción y la distribución de equipos geotécnicos y geofísicos patentados para prueba in situ. Sus actividades de investigación se desarrollan principalmente en cooperación con la Universidad de Alquila y también con otras universidades e institutos de todo el mundo. Es coautor de más de 70 publicaciones en revistas técnicas y conferencias. Diego realizó presentaciones técnicas en más de 70 países en conferencias nacionales e internacionales. Bueno, sin más que decir con la presentación, le doy el pase a mi colega, la ingeniera Shirley Suárez, que se encargará de dar la presentación en inglés. Ingeniera, es todo suya la pantalla.
Muchas gracias, ingeniero Sandro. Vamos a hablar. Now, let's talk about your experience, Engineer Marchetti. Okay, we can start presenting you as the engineer with a degree in computer science from the University of Pavia in Italy. You have worked since 2001 in association with Professor Silvano Marchetti, who is the creator of the Marchetti Dilatometer, DMT, on the 1980, used in more than 80 countries around the world. It's a big work. Together, you two developed potentially seismic dilatometer, Sdmt, in 2004, and the automated dilatometer, Medusa DMT, completed in 2019 and used today in four continents. In past years, they funded Studio Prof. Marchetti, a company that consists of the design, production and distribution of patented geotechnical and geophysical equipment for in-situ tests. Your research activities are developed mainly in cooperation with University of Alquila and also with other universities and institutes around the world. You are an author and co-author of more than 70 publications in technical journals and conferences. Diego made technical presentations in more than 60 countries and national and international conferences. With this now, we have to show the respect for your father, and all your work has been really important around the world, as you was shown, and you have the legacy for this, and we all know that you might be so proud of, and that's why we want to show all the respect that he deserves, and we have the same for you. Now, Engineer Marchetti, that we have shown all the respect that you deserve, and your father too wants to rest in peace. We can start sharing your screen. You can start sharing your screen, please.
So, good morning to all of you, and thank you so much for this very nice introduction to the history of the DMT in terms of my father, Professor Marchetti, who invented the dilatometer from scratch, and also of myself and of our 30 years of study and work together. So today, with this presentation, the aim is to give an introduction on the Marchetti dilatometer and seismic dilatometer, and also the Medusa DMT, to show you how the equipment works and how it can obtain geotechnical parameters, the processing of the results, and some applications to design. So we will see several applications for which this equipment and its results are used every day in geotechnical practice around the world. So again, let me pay a tribute to Professor Marchetti, my father. He passed away in 2016. You may see him with the most important people in the world of the geotechnical world, Mike Yamalkowski, John Schmertman, Roger Frank, and others that you can see in these slides. And I wanted to put a nice picture of myself with him at the conference that was in 2015 in Rome. So let's go into the technical part. Please, if you have questions, write them down so we can all have a nice session at the end of the presentation and to discuss whatever you would like to talk about. So as an introduction, let me tell you that in penetrable soils, direct push technology is taking over laboratory and SPT. By direct push technology, I mean SCPT, the S is for seismic CPT, and seismic DMT. The reason of this is that it is very simple, it's fast, it provides repeatable results, continuous soil profiles with depth, and real-time results. In sands, recovering undisturbed samples is very difficult, so direct push technology is the state of practice. Now, the seismic dilatometer I want to introduce is the combination of the flat dilatometer invented by Professor Marchetti in 1980 and the seismic module for measuring the shear wave velocity and also compression wave velocity. These two instruments can be used alone or in combination with each other. And we will see that the seismic has also been combined with the CPT. Let's start with the DMT first. The DMT is a stainless steel blade with a flexible membrane mounted on one of its sides that you see on the right side of this slide. The diameter of the membrane is 60 millimeters. The test consists in advancing the blade into the soil using penetration rods for pushing the instrument and a penetration machine for advancing the instrument in the soil with pressure. A pneumatic electric cable runs from the control unit at surface into the rods and down to the blade at depth. A gas tank is necessary to provide the pressure of air, or even better with nitrogen, but you can use either one. A computer may be used in case you want to obtain real-time processing of the results and see already the results. If not, you can simply write them down and take the pressure readings from the control unit without the computer. Now, the test procedure consists in advancing and stopping every 20 centimeters. As soon as the blade is advanced and stopped, initially, the total horizontal pressure of the soil will flatten the membrane against what is behind it, a support behind it. The operator will use the valve on the control unit to inflate the pressure and the gas that will run in the pneumatic cable and start to inflate the membrane from the inside. When the pressure of the soil is in equilibrium with the pressure of the gas that you are pumping from the inside, the membrane will lift off. So A is called the lift-off pressure, which is basically the total horizontal pressure. B is the pressure that is necessary when you continue to inflate after A without stopping to expand the membrane of 1.1 millimeter in its center. And then the operator has to deflate after B, if not the membrane will overexpand and explode or damage. And if the operator deflates with a slow vent valve, you can take the C reading, which is very useful in sand. The C reading is when the membrane returns in its original flat position before A. So to summarize this, when we push the blade, the soil, which is the red pressure, is flattening the membrane. We start to inflate the gas from the inside, which are the blue arrows. And when the membrane will start to move, there is a contact that will go off and the A reading is taken. The operator continues to inflate, the membrane will expand, and when the expansion is exactly 1.1 millimeter in the center, the contact will go again on and the B reading is taken. It is then necessary to deflate, the signal will go off, and when the membrane returns in the flat position at the beginning of the test cycle, the contact will go back on and the C reading can be taken. So the DMT test consists in taking 2 pressure readings, or 3 if you also do the C reading, every 20 centimeters. Normally up to 20, 30, or even 100 meters. This is a picture with the main components of the DMT, the membrane, which is already mounted on the blade, the control unit, the pressure regulator for the gas tank, the pneumatic electric cable going from the control unit into the rods and down to the blade. This is the Medusa DMT, which is the newly developed fully automated dilatometer. It was designed initially for offshore, but now everyone wants to use it also onshore because it is very comfortable to use compared to the manual equipment. It is composed of a battery power pack, an electronic board, and a hydraulic motorized syringe for generating the pressure with oil. It's composed of an engine, a piston, and a cylinder. Then there is a pressure transducer for measuring the pressure, and a DMT blade of standard dimensions. This instrument is able to perform the readings autonomously, even without a cable, but normally a cable is used to obtain the results real-time during the test. The results are the same of a standard DMT, but taken with more precision and accuracy because everything is automated. The seismic equipment, which has been added recently also to the Medusa DMT, consists in an additional electronic board compared to the Medusa that acquires the signals from a top sensor and a bottom sensor. The test consists in generating a shear wave at surface using a shear beam, which must be energized with a horizontal blow of a hammer against this shear beam to generate the shear wave. The shear wave will travel at depth and arrive to the top sensor and to the bottom sensor. The electronic board will amplify and digitize the signals at depth and send them at surface to the computer. Well, you will see real time these two waves. Of course, the blue wave will arrive before because the sensor is in the top part, and the bottom wave will arrive later. The delay delta t in the arrival of the wave will be used in this formula, where S2 and S1 is the travel path of the wave between the center of the shear beam and the sensors, and the Vs evaluated is the average shear wave velocity in the layer between the two sensors that are 0.5 meter apart. G0 will then be obtained from the shear wave velocity using this well-known formula and the soil density. Just to show you how simple it is, you have to click on the acquisition button, give a hammer blow, like in this video, and you will see in the screen the delay of the wave in the registration, and the system will evaluate the delay and show you how well the delay was evaluated, superimposing the waves, and it give you a real-time evaluation of Vs. Normally, and this is what you see on the screen, normally you repeat 2 or 3 times so that you are sure that you get a very high repeatability, which is below 3, 4, 5%. In this case, it's even less than 1%, the repeatability. And this is done every 0.5 meter because the sensors are spaced 0.5 meter. The main features of the Sdmt are that the execution is quite rapid because you don't need to drill a hole if the soil is penetrable, and you don't need to wait for the cementation of the hole as for crosshole or downhole. You just push the equipment like for the DMT and do the seismic test in addition to the DMT. The accuracy of the evaluation of the delay is very high for several reasons. The first one is that the electronic board is a custom designed acquisition board that digitizes the signals so that when they are sent at surface, the data may not be corrupted and be of very high quality and free of noise. The signals are amplified and digitized at depth, so you have clear waves and a very consistent delay delta t. But very importantly, the system has 2 receivers versus the old systems that have only 1 receiver. If you have 2 receivers, you are looking only at the delay between the waves, the same wave arriving at 2 different depths. If you have only 1 sensor, you have to record a first blow to the first sensor, the only sensor you have, then go to the next depth and be as accurate as you can to give 0.5 meter or 1 meter depth. And if you make a mistake, your VS will feel this mistake of depth, even if it's small. And the wave will not be the same because you have to make a second hammer blow. So this measurement is a true interval or differential measurement because you are comparing the wave arriving to the first sensor and what is needed to perform 0.5 meter more. And so it is very accurate because it's differential. The evaluation of the shear wave is automatic. Often the post-processing is unnecessary and the real-time evaluation of VS is perfectly the final value. Only if you are very close to a power station or a train station where you have vibrations, you have to use a little bit of post-processing to filter the results. But in 95% of the cases, the results you get in the field are already the final results. The test is operator independent, provided that he does the setup as explained in the training that is given, and the results are available real time. The first clients who used the test immediately compared the Sdmt with the cross-hole, and this is an example in New Zealand showing a very good agreement between the VS obtained from the Sdmt and 2 cross-hole tests. A similar experience was done in Brazil by Damasco Pena in 2017, again showing an excellent agreement between the cross-hole VS and the Sdmt in 3 different test locations. The Sdmt was very well accepted by the community of geophysics and shear wave velocity, to the point that we were asked to combine the Sdmt, or the seismic part only, without the blade, also with the CPT. Currently, we have 3 partnerships, and we are working on a 4th partnership with Vandenberg, in addition to GeoMill, Pagani, and Gura Geo, to make the Sdmt cone, which is the CPT with the Sdmt. There is no limit in combination of the Sdmt with other CPT systems, because the seismic is completely independent from the CPT measurement. Now let's look at the machines with which you can normally advance the DMT blade. The DMT can use all the machines that are used for advancing the CPT. In particular, the heavy truck penetrometer, which is the most productive because it is able to push up to 25 tons without lateral instability. Yet it is very expensive. Additional solutions include small penetrometers, like this one you see here used in Costa Rica, that can push the DMT, and it's a lighter penetrometer, but it has to anchor, because if it pushes, and it can push also 15 or 20 tons, but it would go up. So the anchors are used to get the reaction force from the ground. The DMT or Sdmt can be advanced also, well, dynamically, only the DMT, because the seismic can damage if you use all the power of the hammer, but if you use only a small part of the hammer blow, you can even advance dynamically the Sdmt. However, this is not recommended in extremely soft soil, because the disturbance of the dynamic will be higher and have an influence on the results. But if you use the hammer very gently, because the soil is soft, you can advance disturbing not so much and having excellent results. Or using a drill rig from the bottom of a borehole, just like an SPT, but pushing or even dynamically from the bottom of a borehole. You can use basically any method you can, as long as you get the blade into the ground in the virgin soil. If you want to use a drill rig, you have to use this method that was called torpedo. The torpedo is the combination of a blade with an adapter, 3 or 5 penetration rods according to the capacity of the drill rig, and a top adapter for allowing the cable to pass inside the penetration rods and come out from this hole protected against this slot, so that the cable does not damage when it exits. And then the cable is taped to the drill rods. So you drill a borehole to whatever depth you want. Normally you use casing to avoid the hole to close, and then you lower this connected torpedo with the drill rods and taping the cable to the rods, lower it to the bottom of the borehole and push every 20 centimeters. When you reach the full length of the penetration rods, 3 or 5 meters, you then take away the instrument, disconnect the torpedo without disassembling it. You keep disassembled, you only get the cable and put it on the side. Then you drill, you advance the casing, and you continue with the same test cycle below. This methodology is certainly slower than the penetrometer, because you have to alternate the drilling and the measurements. But it is able to overcome obstacles because you can drill them and continue below. Another possibility is to use a drill rig like a penetrometer. We can supply you this mechanism, which is called the shaka, that has an adapter from the diameter of the drill rods to the penetration rods, then a slotted adapter for the cable to exit, and you can add penetration rods and push. This is an example of a video we did in Chile, just to show you how it is possible to advance. In this case, it was also seismic, so DMT and seismic, and we did a test in this soil that you are looking at with an SPT tripod. Another example is to do the test offshore from a floating barge. In this case, you have the Sdmt and the seafloor hammer. This barge was anchored at the four corners with buoys. And then using a drill rig, we did test up to 50 meters of water, also with the hammer taking the shear waves. This is a more recent test in Vado Ligure, northwest of Italy, in full COVID, May 2020. And we did the test from this floating barge, again with a drill rig and with a hammer for the generation of the waves. Just only 2 weeks ago, I was on this jack-up in the harbor of Barcelona. We lowered the hammer from the jack-up, and we did the test using a drill rig and this guide tube where we push the rods inside this tube because we had 17 meters of water and you want to have a guide of the rods down to the seafloor. Last year, in November 2021, we did an expedition in the North Sea, 1,000 meters from the North Pole, and on this big boat, and we were ready to, we integrated the Medusa DMT with the Manta, which is a GeoMill seafloor equipment for operability up to 1,500 meters. And the data transmission passes through a cable, the same cable that is used to operate this machine from the surface. Now let's see the type of soils for which the DMT and Sdmt may be employed. The DMT can be employed in all penetrable sands, silts, and clays, where the grains of the material are small compared to the diameter of the membrane. This means from very, very soft soils with low values of strength and moduli, up to hard soils, up to almost soft rock with high values of strength and moduli. The blade itself is very robust and can withstand a push of 25 or even 30 tons. The weak point is not the blade, but the rods. Of course, you are not interested to do a test in concrete like this block, but it's just to show you that the blade will not break. You will first break the rods or the membrane, but the membrane is very simple and cheap to replace. The Sdmt is also performable in all sands, silts, and clays, but also in non-penetrable soils like gravel or very dense sand. Of course, the Sdmt is only the seismic without the blade. In this case, you have to drill a hole, and then inside the hole, you backfill it with a rounded gravel, and you can read some details in this publication, even though we updated the test procedure, but this is the principle. And you can do it also in non-penetrable soils. The max depth we reached was 135 meters in the town of L'Aquila in 2009, after the terrible earthquake that occurred. Now let's look at the interpretation of the results, first of the DMT and then of the seismic. So we said that we come from the field with DMT readings that are 2 or 3 pressure readings every 20 centimeters. How do we obtain geotechnical parameters for design? How can we use this information? So the first step is to apply to the field readings the correction of the membrane. The membrane has a rigidity, and through a calibration that evaluates delta A and delta B, which are basically A and B readings out of the ground. I'm not going to go in this technical detail, but you correct the A, B, and C so that you eliminate the steel rigidity of the membrane and get the clear corrected readings of A, P0, B, which is P1, and C, which is P2. The second and most important step is the definition of 4 intermediate parameters. And the nice thing is that each one of these has already a meaning of the soil. The material index for information on soil type, the horizontal stress index KD, which has information on stress history and horizontal stress, the dilatometer modulus, which is related to the modulus that you can use for settlements, and the constrained modulus that we will see in the next slides, but it's not directly usable ED, but it is a modulus. I will explain this in the next slides. and UD, which is a parameter coming from the C reading, the corrected C reading is P2, for distinguishing between drained and undrained soils. Now, the second step, or the third step, the most important, is to use correlations, so not definitions, from the intermediate parameters to the final interpreted geotechnical parameters that we know well because we use them in soil mechanics. These were obtained by Professor Marchetti when he went all over the world in many research test sites that were very well documented. And so he constructed processed the best correlations to these parameters using the information contained in these four intermediate parameters to get the constrained modulus M, the undrained shear strength in clays, the earth pressure coefficient in clays, the overconsolidation ratio in mainly clays, ED less than 1.2 is clays or silty clays, friction angle in sands, and the unit weight and soil description in all soils, the pore water pressure in sand or excess or pore water pressure in clays, and distinguish between drained and undrained materials. So a lot of information, and I will show you how this is obtained. These are the formula, of course, I'm not going into them, but divided very well in the field readings, A, B, C, delta A and delta B, which are the calibration, and the dissipation test that I will introduce later on. The corrected field readings, P0, P1, and P2, the intermediate parameters, ID, KD, ED, and UD, and the flex point of the dissipation, and the interpreted geotechnical parameters that we use in soil mechanics. On the right, you see a chart for the soil behavior type. So at each depth, you have ID and ED, and this chart was published in 1980 and has proven to work very, very well. So it is still used today exactly as it was to distinguish between clay, silty clay, clay silt, sandy silt, and so on. And the number in the box represents the unit weight of the soil expressed as the ratio unit weight of the soil over unit weight of water. So 2.05 means that the unit weight is 2.05, the unit weight of the water. Now let's look at the intermediate parameters. ID contains information on soil type, and you will see this because if you do a test and you do the A and B readings, or P0 and P1, you will see that the ratio P1 over P0 is about 1.1 to 1.3. Whereas if you are in sand, the ratio is about 2.5 or even more. In silts, it is somewhere in between. So ID has been defined as P1 minus P0 normalized to P0 minus U0. And it distinguishes very well clays, silts, and sands. Let me show you an example. This is a test site with sand and clay. In sands, you see 2.61, 11.90. So it's very clear, this ratio of 4 to 5, indicating sand. Let's look at depth 19, for example. The ratio 665 over 586 is about 1.1, 1.1. Okay, so very clear. This is a log scale indicating that it's very well distinguished between the two. And of course, the silt falls somewhere in between. The second intermediate parameter is the KD, or stress history index. The formula is the same as for K0. You see, P0 is basically the total horizontal pressure of the soil against the membrane minus the water pressure, so it's the effective horizontal pressure, divided by the effective vertical pressure. So that means that KD is equal to K0. Unfortunately, it's not true because you have penetrated with the blade and you have created an extra horizontal stress. So P0 is not the total horizontal stress. However, in clays, this is the closest measurement you can do to K0, to get K0, and KD is very well correlated to K0 and OCR, and I will show you this in clays. In sands, It's not so simple, and I will talk about this later. So when you are in a normally consolidated clay, Kd is equal to the value of 2. It's not small in general. It's equal to the value 2. In over-consolidated clays, the value is higher, and the more it is high, the higher is OCR. Let's look at an example. This is a test site with silt, sand, and clays, and then a clay, a silty clay. You see in the top part, Kd is very close to 2, and this is a normally consolidated layer of these different types of materials. And below 14 meters, Kd is much greater than 2, indicating this well-known over-consolidated silty clay. Now, Professor Marchetti, using experimental data he collected in the 70s, published this formula in 1980 as a function of Kd to obtain OCR. There are several publications, among which this one in 1995, so 15 years later, showing a very good agreement between the correlation obtained from Marchetti in 1980 and the best fit of many other additional points. And you see that the best fit line, which is this continuous curve, is very close to the dotted line, indicating a good agreement. Additional validations were obtained through theoretical publications by Fino and Yu, showing again a very good agreement for this correlation between Kd and OCR, using very advanced and sophisticated models of the soil. The same approach was used to obtain the estimation of K0 from Kd with this experimental formula. And as you can see, the values are very close to these lines, this curve, showing a very narrow dispersion of the results and a very good agreement in clays. And this is a part of the same study I showed you before for OCR, published and presented by you in Porto in 2004, showing the good and the validity of this formula between Kd and K0. An example of this was used in one of the first jobs where I was working with Professor Marchetti. There was a very important landslide close to a railway, and the interest was to study the total and the effective horizontal stress. So we did 3 DMTs close to the landslide, a bit farther and very far away to have a reference. And as you see, the 3 curves obtained by K0 multiplying sigma prime in the vertical direction, we obtained the 3 curves that were very, very clear to detect the relaxation of the horizontal effective stress. The third intermediate parameter is ED, which is defined from the theory of elasticity. It's the elastic modulus obtained from the horizontal load test performed by the membrane expansion. So with this geometry, which is well known, and accepting the elastics theory that you can find details in this publication, you obtain this formula, ED equals 34.7 times P1 minus P0. Now, this modulus is not directly usable for many reasons, because first of all, it's in the horizontal direction, not in the vertical. Then the soil is disturbed because you penetrated with the blade. Certainly, you disturbed less than with any other equipment, but you still disturb the soil. And finally, it is a undrained modulus, at least in clays, while the constrained modulus is a drained modulus. So the final constrained modulus you get from the DMT is obtained from the ED, which is limited and defined to the dilatometer modulus, corrected with ID and KD, because the soil type provides information on the amount of drainage in order to fill the gap of the fact that ED is undrained and the M is drained. So the correction of ED on ED is different if you are in sand, in clays, or in silts. And the KD is the stress history or horizontal stress, which helps to fill the gap of information between horizontal and vertical stress. So these three ingredients are well used in the formulae that were found by Professor Marchetti to use all the information available with the DMT to estimate the constrained modulus. There are many publications in literature showing excellent agreement between the constrained modulus M obtained from odometer data and from the dilatometer, showing very good agreement. I'm representing here three continents: United States, in Norway, and Japan. You see in Norway, the profiles are the ones between the shaded area, and the points, which even have some dispersion, are from odometer test on samples. And on the right, you see the test in Japan, again with the odometer showing excellent agreement. For what concerns the strengths, in clay, the formula used to estimate SU is the Chance-Sepp relation, which tells us that the ratio between SU and effective vertical stress in an over-consolidated soil is equal to the same ratio of the normally consolidated soil times OCR to the power of M. We have seen the estimation of OCR from KD with this formula, presented a few slides before. The exponent M is around 0.8, as pointed out by Professor Ladd, and well known in literature, and the ratio between SU and sigma prime V in normally consolidated clays is generally 0.22, 0.23. So if we combine all this information, we obtain a single equation for SU as a closed formula function of KD and effective vertical stress. Again, you may find several publications showing excellent agreement between the undrained shear strength obtained from the DMT, which is the black thick line, from other tests like pressure meter, triaxial test, and CP2 with a constant for this SU. And these are research test sites where the quality of the test is very, very high. Another publication in Canada obtained with a field vane test showing a good agreement. And finally, again, in the same Japan territory, in triaxial tests and the DMT, where the profile of the DMT passes right through the points of the triaxial tests. This is the research test sites in Italy, where you see the various interpretations of SU from a laboratory and from field vane tests, and also from the CPT, where according to the NC value, you have these different profiles. The DMT, fortunately, does not require, has the formula that I just showed you without requiring any type of correction. Now let's look at the C reading. We said that the C reading consists in deflating after B with the slow vent valve. And why is it useful? Well, it is very useful in sands because it provides the water pressure, as you can see in this drawing, in this slide. Basically, when the membrane slowly returns after inflation, in sands, the sand will remain where it is after the expansion of the membrane, and only the water will push the membrane back to close in the original position. So when you are in sands, the corrected C reading will lie on the water pressure, which in this particular case, published by Schmertmann in 1988, shows that is hydrostatic. Then when you get to clays, it does not work because the membrane expands in clays, but then when it returns, the clay comes back. And so you have an extra water pressure and is well highlighted by the C reading. And as you get closer to the sand, you see that the points feel the drainage and again lie on the hydrostatic line in this example. So when in sands, P2 is equal to the water pressure, whereas in clays, P2 is generally greater than the water pressure and highlights the excess pore water pressure. So UD is defined as the distance between the point and the water pressure, which is 0 in sand, and in clays is greater than 0. Just to show you an example, here we are in the harbor of Catania, southern Italy, and the test was classified as silty sand. Now the material. And we did see readings every meter in 5 test locations, and they all lied very nicely on the hydrostatic line. So we inferred with UD equal to 0 that the behavior was fully drained. Now let's look at the last measurement you can do with the DMT, at least with the standard equipment. With the Medusa you can do some others, but we don't have time to look into them. The idea is to do dissipation test for estimating the coefficient of consolidation and permeability in clay. The test consists in advancing the blade just like a normal test reading, and you stop. At that moment, you have created an extra water pressure due to the insertion of the blade, which increases the horizontal pressure, and in clays creates an extra water pressure. So the time starts when you arrive at the test depth, and you repeat only A readings, which are basically the total horizontal stress, without expanding the membrane. So you have time and A, and the blade is not moving, of course. We already created the excess pore water pressure. We want to see how fast the water dissipates. So if you take the readings at double of the time, because the scale is a log phenomenon, it will design an S-shaped curve and create a flex point that has been correlated to the coefficient of consolidation, as you can read in the publication of Totani et al. Many years ago, and now it is well accepted. From that, you can obtain also the coefficient of permeability, KH, as a function of CH, gamma water, and of course, the modulus that you can get from the DMT. You can do the test also with the cone, of course, and we compared several dissipations, but the main difference is that, first of all, you disturb the soil less with the penetration of the blade. Second, you don't measure in one point, but you measure in a larger point, in a larger area, like a small embankment. So it's very similar to the consolidation and permeability of a small embankment in front of the blade, which makes it reliable because it's not only a single point, but an average like of the bulb of the soil involved in the membrane surface. As a historical note, let me show you comparisons of this CH with laboratory results of high quality in this real case project that has been published, and with the back calculation after the construction showing excellent agreement between all the 3 values. Today, with the automated Medusa, we don't need to take only points. We have a full continuous, very high resolution A readings, and we get the full curve automatically without needing to take the readings with manually. And you have the full curve, and the flex point provides you the coefficient of consolidation, and from that, the permeability. This was an example of the dissipation test offshore we did in the harbor of Barcelona. I showed you a few slides of that. You see how many readings we take with the Medusa. These are seconds, basically, are 4 or 5 readings per second. This is a log scale, so this is 1/100th of a minute, less than a second. So we get a lot of points. And this was 35.5 meters below sea level. The DMT is encoded in the European standards according to the Eurocode 7, to the ISO standards since 2017, and American standards since 1990, but there has been several revisions and updates. The most complete document is, however, this TC16, which is called this way because it was written by the Technical Committee 16 of the International Society of Soil Mechanics and Geotechnical Engineering Committee. Today, this committee changed name to TC102, but the document is called TC16. And it contains 41 pages of the testing equipment, the test procedures, and the processing of the results, most of which I addressed in this presentation. There are several other standards, but national, that you can find in Italy, Sweden, France, China, and maybe in some other countries. The DMT and Sdmt are owned in many countries around the world, mainly in North America, Europe, Eastern Asia, but it's increased a lot in Australia and New Zealand. There are many, at least other 20 points in this area and also in this area, and we have to update this graph. In Africa, there are not so many, even though there are 4 or 5 points more, because many European companies go there with the equipment and do the tests. These points are owners of equipment, not testing sites. Now let me show you some results to get confidence with how to read the graphs you obtain for geotechnical design and for geotechnical applications. Here we are in a test with clay near the airport, Fiumicino, in the new, where they constructed the new exhibition center, but not quite well. Here we are inside the pavilions. We did a test inside. And the reason of the test were that they had a lot of problems because they put the perimeter on piles and then they did not do a good job for the rest. They dug out and put gravel, but I don't have time to go in these details. I just want to show you the results. These are the P0 and P1 readings, so maybe you can already predict that we are in clay mainly because the readings are close to each other and not far apart. Maybe here we have some sand, but we will see this later in the intermediate parameters. These are the field readings corrected with the calibration. The C reading, you can immediately see that the excess pore water pressure is in clay and you have some nice sandy layers that define also your water hydrostatic line. And this is the unit weight obtained with the chart I showed you before. So this is the input and field readings. Now let's look at the intermediate parameters, ID. Clay, silt, and sand. You see it's mainly clay, but some layers of sand that are confirmed by the UD, where the UD is equal to 0. It means that P2 or the C reading is on the hydrostatic line and you have UD equal to 0 with a fully drained behavior. But most of the soil is clay and undrained. So material index and pore pressure index are independent, but they confirm these sand layers quite well always. This is the horizontal stress index that is equal to 2, indicating that this clay is normally consolidated, whereas in the sense KD equal to 2 does not tell me if it's normally consolidated or not, dense or undense, but the higher the KD, the more it is dense. But there is not a direct correlation with OCR. You can see the differences, but not the absolute value of OCR and K0. ED is the dilatometer modulus, and UD, we already talked about that. The geotechnical parameters you see are the soil behavior type. So the red is still the plot of the ID that we already saw, but you see layer by layer for each depth, according to the chart I showed you, that you have a little bit of silt in the top and then clay with some layers of sand, which are more yellowish. This is the constrained modulus using the formula I showed you before, the undrained shear strength, which in this normally consolidated clay is growing diagonally with depth. The friction angle where we have a sand. And again, we replot KD to see the stress history, even though it's an intermediate parameter. Then, thanks to the correlations in clay, we have an estimation of OCR, which comes out OCR equals to 1 because KD is equal to 2. And here we have a very hard crust with extremely high values of OCR. And then again, K0, which in the clay is 0.5, as you see here, except in the top crust where it's higher. And this is, of course, the effective horizontal stress obtained from K0 times the vertical effective stress. And this is the profile. We also did a dissipation test at 35 meters, and in this case it was very slow because it's clay, as you know, in the profile from the profile before, and T-flex is around 100 minutes, and this is the coefficient of consolidation and permeability. Now let's look at an example of these tests in clay, silts, and sands, not only mainly clay. This is a paper factory in the northeast of Italy. They have to construct another building in this area here. So we went with our truck and did the Sdmt tests with the Medusa. Here it's even nicer to see the clay and the sand. You see the sand is when the second reading is much greater than the first one. So this is sand, confirmed by the fact that P2 is on the hydrostatic line. And then when the readings are close to each other, you have clay confirmed independently from the C reading because you have excess pore water pressure. And the same here, you see clay, excess pore water pressure. Readings are far away, sand confirmed by the C reading. And this is the unit weight. This is more visible in the intermediate parameters. So this was the sandy layer we saw before, the clay layer, and so on. These parameters come directly from the comment we said already. KD is greater than 2 in the sand, so probably the sand is quite dense, and the clay is mostly normally consolidated because it's equal to 2. And the dilatometer modulus, the one we have to correct to obtain the constrained modulus, and again the UD, where we have UD equals to 0, it's fully drained behavior. Where we have higher values, it's undrained. This is the main graph with the soil behavior type. So with the colors, you see the type of soils. This is the sand layer we saw before with the clay and some clay layers, and the constrained modulus, the undrained shear strength when you are in clays or silty clays, the friction angle when you are in sand or silty sand. And again, we repeat the KD for the stress history and the shear wave velocity, because we did also seismic waves with the Medusa. This was a test in the northeast of America in the, for a bridge project. And this was the seafloor system that with a seafloor hammer for generating the shear waves. As you see, the soil was very soft for the first 15 meters. And then there was gravel that we had to drill and go on below for a silty clay that had this profile with the DMT. The nice thing was that they did also test with the pressure meter and with the CPT. They actually calibrated the alpha value of the CPT using the DMT and the pressure meter. And here you see an excellent agreement between the test for the modulus and also for the undrained shear strength. Now let's see what are the main differences between the DMT and cone-shaped probes like the SPT and CPT. For what concerns the CPT, one of the first differences is that the CPT test is performed during what should be a fixed penetration rate of 2 centimeters per second, which means that you have to impose, monitor, and make sure that you are respecting. This requires necessarily a penetrometer, and the penetration rate, if it's very much different from 2 centimeters per second, can influence the results. For the DMT, there is no specific requirement on penetration rate because the measurements are performed when the blade is not moving. So it doesn't really matter how fast you go at depth, to the test depth. We are doing an advanced research for a small family of silts where this statement is not true because it's partially draining material. So it's a small family of silts. And if you go fast, you get higher readings. If you go slow, you get lower readings. But in clays and sands, silty clays and silty sands, and most silts, you don't have influence of the penetration rate. And the measurements are independent of such rate. And for this reason, you can use not only the penetrometer that you use for the CPT, but also the drill rig, SPT hammers, or any machine from a floating barge that is going up and down, as long as it's anchored for not moving horizontally. A second important difference between the DMT and the CPT-shaped probes is the disturbance. We already saw the slide. When you penetrate with the cone, you disturb because you fail the soil. With the blade, you cut it and only slightly disturb what will be in front of the membrane. So the DMT during penetration preserves better the original state of the soil. So the soil parameters are more representative of their original state and do not require a correlation to fix from this damaged soil to what was the original natural soil. Another important point is the horizontal stress. As published in this publication in the Canadian Journal, when you penetrate with a circular probe, you generate a very stiff pre-stressed cylinder, which comes directly from the well-known arching effect, like when we do tunnels. But in this case, instead of the tunnels, it is an obstacle to the horizontal stress because this stiff pre-stressed cylinder does not act on the shear, on the friction sleeve of the cone, and therefore it's very, very insensitive. The relation between the width and the thickness of the blade is such that the arching is very, very small in the section, rectangular section of the blade. So there is very little arching. And furthermore, we measure the soil in the horizontal direction, filling completely the total and effective horizontal stress. The fourth difference I want to show you is through an experiment published by Lee in 2011. They reconstituted samples at different relative densities, about 40%, 60%, and 80%, and then they put the exact number of the relative density. And then they performed a CPT and a DMT test. And they saw that the CPT was very good in estimating the relative density, but was totally unable to distinguish between normally consolidated and over-consolidated samples of soils. They performed the same test with the DMT, and the KD values aligned quite well on parallel curves that were going towards the upward direction in this graph as OCR increased, indicating a high sensitivity to OCR. Well, this is a very scholastic and academic example to show that you can have three very different soils that have the same strength, but different stiffness. And stiffness and strength are very different. So if you measure strength, it's very difficult then to find the factor for without other independent information for obtaining which stiffness corresponds to the same strength. This is the shear strain curve from the modulus G0 and the strain. This slide was published by Main, but confirmed also by other authors, showing that in the range for deformation analysis is where the flat dilatometer provides you the modulus, and also, of course, the unload and reload of the pressure meter. Instead, tests like SPT and CPT that fail the soil, they are in the range for bearing capacity, so for rupture. But then, to obtain a modulus, they have to find a way to estimate a factor for obtaining from that the modulus. Now, this concludes the initial part of the presentation concerning the equipment, test procedures, and interpretation of the results. Now I would like to address several applications for which the DMT is used worldwide in everyday projects. The reason is not to tell you that the DMT can solve all your problems, but I just want to show you how people use the results so that if in case you have similar projects and you have a DMT profile, you know what was done already by others. The first application, and by far the main application for which it is used is for the modulus, for example, for settlements. We all know that a settlement is obtained from the load, where we could use Boussinesq to evaluate the excess stress caused by the load, and the modulus we can obtain it from the DMT, and even with a very simple monodimensional formula, we can have a very average value of the settlement. Professor Marchetti used to say it's better to have an approximate, to be approximately right than precisely wrong. So a simple formula, monodimensional, instead of precisely wrong with decimals and a lot of expressions to take into account many secondary factors when maybe we make a mistake with the modulus m because we estimate it wrongly, and then have a very big estimate, a very big error due to the modulus. You will find in literature many case histories showing very good agreement between the measured and DMT predicted settlements or moduli, and these are examples of publications. Just to show you a few, this is a comparison of observed versus DMT predicted settlements, showing a very good agreement of the observed settlement with the curve of the DMT, where the SPT predicted with a very unconservative value, even though if you read the paper, you will see that they made even a mistake in using the modulus, but definitely the SPT contributed to have a very incorrect value of the settlement evaluation. Another example is in Serbia, in this case in Belgrade, where this foundation settled a lot. The DMT predicted 77 centimeters, while the measured was 63. This is the profile of the modulus in blue, and the red points are measured points where they measured the deformation and back calculated the modulus, showing an excellent agreement between the modulus from the DMT and of the points. This is a collection of 28 structures that settled, and these were settlements obtained from DMT predictions and settlements obtained from the measured settlements, showing a very, very good agreement on R squared of 0.9509, which is very high, in very different soil types, but always in structures with shallow foundations. This is another collection of 107 projects where this user of the DMT published in Budapest in the last ISC International Site Characterization Conference, more than 100 projects where the DMT test data saved the owner money over the previously overly conservative design based on less accurate tests. So basically, for example, with SPT, they predicted to have to do deep foundations. With the DMT, they predicted a higher modulus and were able to do shallow foundations, for example. And this is the sum of the saved values in all these projects. Now, just to show you, this were example of tests performed in Bogota, in Colombia, in 2015 at the Escuela Colombiana. Some of you may have been present at the time, while myself and Professor Robertson were doing the presentations similar to this one inside the main hall. Outside, they were doing tests with the drill rig and with the DMT and Sdmt equipment. This is the profile that came out with showing basically a clay with a quite heavy crust that was not shallow. It was up to 5 meters, and then the soil was extremely soft clay, and the modulus increased triangularly with depth. This is the undrained shear strength that was obtained. The KD was with the value of 2 from 8 meters onwards and much higher at surface. And this was the shear wave velocity. As you see, there is a very dense top crust in the first 8 meters. And that's why OCR and K0 are very high. And then in the clay, OCR is equal to 1 and K0 again equal to 0.5, which is typical of normally consolidated clays. We decided to do an example of settlement prediction with a rectangular area. This is a software that is free, provided by us online, where you define the load area, in this case a rectangle with these dimensions and this uniformly distributed load, and the base was dug up for the first 2 meters. And then you can import the soil parameters, in particular the modulus every 20 centimeters, and you immediately have an evaluation of the estimation of the settlements in the center, in the 4 corners, and in the median sides of the long side and the short side. You can also access the graph where you have the modulus that we already saw from the DMT test, the Boussinesq evaluation of the increase of stress from the 2 meters that we dug out. And then you see the deformation. And from that, if you integrate the settlements, you obtain a settlement at the top of 225.5 in the center of that load. Now, let's look at another application, G-gamma decay curves. Now, we already saw the graph of the decay of the modulus G with a strain, and we already saw that the DMT provides a modulus in this area. So with the seismic test, we have Vs and therefore G0, so we have the first initial point. And with that, and using the DMT modulus, we can try to estimate the curve. If we have a low ratio G0 over M, it means the curve is more like the top curve. If we have a high value G0 over M, then the curve will decay quite rapidly. So there have been several studies on this, and Dr. Sara Amoroso in 2014 published this research. She did in several test sites from laboratory. She used intersection because she knew G0 from laboratory and found that the gamma from the DMT was at certain points. And here she put all the points of sandy sites and silty and clay sites. So as you see, the gamma DMT for sand is a little bit lower, while for the clay is a little bit higher. And this was allowed to make an estimate of the G-gamma decay curve on site using VS and DMT data and with this hyperbolic curve. We don't have time to go into this, but the first validation curve worked very well. Additional work will be shown maybe later in this presentation. And of course, further validation is required. But yes, it's a very interesting application, especially for those numerical modeling programs like Plaxis that require this type of input. Now let's look at another application for which the DMT is used. And the DMT has been increasingly used in compaction jobs to quantify the gain of the soil improvement, let it be a ground reinforcement, a ground improvement, or with ground treatment. So this was the first publication in 1994 by Professor Van Impe and et al. And they did a test before and after the vibrocompaction, and they saw that KD increased 4 times, while the modulus M increased 10 times in the compacted area before and after compaction. And the nice thing is that they were able to show that the compaction was efficient only up to 8 meters, because below that, the profiles were then the same. Another example in the United States for a project in this school, they did resin injections and wanted to check that between 1.5 meters and 3 meters, 4 meters, they had an improvement of the soil in terms of KD and of M. Another example is in this island in Dubai. You may have heard about the Palm artificial island created with basically with land reclamation techniques, with ships pumping sand and then compacting the sand. And they wanted to ensure that the sand was well compacted. So they did the DMT and CPT tests, and they found the profile of the CPT and of the DMT. And unfortunately, they had not done the test before compaction, which is the best practice, but only after. In that case, you may read some papers to show that the ratio between the modulus M and QT from the cone provides a technique for evaluating where the compaction was good when this relation is above 10, high quality compaction, and where the quality, the compaction quality is poor because the ratio is below 10. This is another example of exactly the same type of project. You can read these 2 publications. You see again a value of 12 to distinguish between the well compacted and or over consolidated and not compacted, normally consolidated. So, as a rule, for good practice of quality assessment of soil improvement, when possible, do DMT and SDMT before and after the treatment. So you can compare before and after profiles of KD, M, and also of VS to see the small deformation G0 modulus changes before and after the treatment. When you cannot perform the test because it's too late, you have to do both DMT and CPT and look at the ratio between M over QT, which must be higher than 10 or 12. Another example that I want to address, in case you have it in your area, is the slip surface detection in over-consolidated clay slopes. When you have a sliding, you have a remolding of the slip surface, which reconsolidates under its own state. So if you do a DMT test in an over-consolidated clay slope, you will have a value of KD, which in general will be high. Then, in correspondence of the slip surface, you will find KD equals to 2. Not a low value, but KD equal to 2, because it reconsolidated and it is a normally consolidated clay. And then it may continue with the healthy over-consolidated clay below it. This procedure was very well documented. I already summarized some of these, commenting the slide before. So basically, you can detect slip surfaces that are quiescent, which could reactivate. And this you cannot with inclinometers, because the inclinometers can monitor if the slides are moving, which the DMT cannot. But the DMT can monitor if there is a quiescent slip surface or it's about to trigger. So in many cases, DMT and inclinometers are used in combination, or the KD profiles are used to localize the inclinometers. This is another published example of a real case project, and you see the high over-consolidated clay above and below, and then when KD is equal to 2, you have a documented slip surface. Another example in this case, you see the normally consolidated, the over-consolidated clay below 12 meters, and many values of KD equal to 2, because this was a very remolded with many multiple landslides above. A very fortunate case was this one published by Herman Pfeiffer in Australia at the IC5 conference. He had by chance done a DMT profile several years before, and then a landslide occurred. He went there back and did the test again and found that at 4 meters before it was greater than 4 KD, and after the landslide it was equal to about 2, indicating the correct depth of the landslide. There was a project in Kitty Hill, a very important one, because a new building had to be constructed on an over-consolidated clay slope, and there were several uncertainties on the slope stability. So they decided to repeat many DMT tests, not only where the building had to be constructed, but also above and below. And it was nice that they found that above all the landslides, they found KD much greater than 2. You see greater than 4 and greater than 6, or yeah, 6. And then where there were the landslides, many values of KD equal to 2, indicating the infected clay area due to the many landslides. And then again, on the rightmost side of this area, they found additional healthy clay. This project was then mentioned in the in a important lecture, the ranking lecture, where you see they mentioned exactly that Kitty Hill I was talking to you about, and mentioned the Totani publication in 1997. So it's a very well accepted method for the detection of slip surfaces. Now let me show you another possible application, which is the design of laterally loaded piles, in particular for the estimation of the PY curves. Now, the original stimulus for developing the DMT was to obtain tools for measuring parameters for the design of laterally loaded piles. When Professor Marchetti was a consultant and he was designing piles, he felt that he had no instrument to monitor the horizontal stress. And as you see, there are similarities between the DMT and the laterally loaded piles. Anyway, there are several methods for estimating the PY curves. The first one was published by Gabriel and Borton. You can find the publication even on our website. Then two additional methods were extended by Robertson and Marchetti, and these are the two recommended methods. The Robertson method is both for clays and sands. He did an adaptation of the PY curves with laboratory soil properties obtained and inferred from the DMT. The method from Marchetti is valid for clays only, and it's a straightforward procedure for deriving PY curves directly from the DMT, bypassing the step of estimating laboratory soil properties. Just to show you the approach, basically the PY curve is obtained with PU as a function of P0 minus U0 for the shear strength, and the stiffness is evaluated as a function of ED. And these are the details that you can find also in literature. These methods were applied to a real case project where Professor Marchetti was consultant. It was a pile of 57 meters with diameter of half a meter, and the lateral horizontal displacement in millimeters was measured with the plus signs, and both the Robertson and the Marchetti methods were almost very similar, showed excellent agreement with the measured values. In case you have to deal with diaphragm walls or an application similar to that, you can consider to read this paper, which describes a tentative correlation for obtaining the Winkler model springs for the design of multi-propped diaphragm walls directly from the parameter MDMT. It also contains indication on how to input the moduli for Plaxis hardening soil model based on MDMT. And in particular, later published also by Schanz and Vermeer, they recommended for the hardening soil model to use E50 ref equals to E odometer ref equals to the modulus MDMT, whereas for the E unload reload, you can use 4 times the modulus MDMT. This methodology was used much more recently and published in this very nice paper of Di Mariano for the excavation of a train station in Barcelona for the high speed. And they did a good modeling, a very interesting modeling with Plaxis of the soil parameters, employing the modulus from the DMT. Basically, they approximated because there was a significant variability due to the fine interlayering of silts, sands, and clays. So they used this approximate red profile. And then with the laboratory, they were able to ensure the G or G0. And they used these expressions here for the input of the hardening soil small constitutive model. If you want more details, read this publication. Finally, I want to spend the last moments for talking about the estimation of CRR in case of a liquefaction risk assessment. Now, we all know well that liquefaction occurs if a CSR is less than the cyclic stress ratio is less. No, I think it's the other way around, actually. If the stress ratio is greater or equal than the resistance ratio. Sorry for this mistake. Basically, the cyclic resistance ratio can be estimated from the CPT, SPT, VS, DMT, and laboratory, whereas the stress ratio is given by this well-known formula that comes from the action, basically, generally of an earthquake or some other phenomena. Now, it is well known that OCR has and aging has a strong influence on CRR. And also aging in sands has a strong contribution due to chemical factors like post-sedimentation cementing bonds and particle contacts, and also mechanical factors due to the slippage of grainage of the grains during secondary consolidation. It is definitely necessary to account for stress history and aging to obtain reliable results for liquefaction resistance. The correction factors depend also on the age of the deposit and are site-specific. So since there are so many factors, it is good and preferable to use more than one testing tool to estimate CRR. Now, a major obstacle for laboratory is to obtain undisturbed samples, because unless you use very non-routine sampling techniques, which are also very expensive, like ground freezing and gel push sampler, it is difficult to obtain undisturbed samples, especially in sands. And also the adequacy of using reconstituted sand specimens, even if exactly reconstituted at the same in-situ density, is questionable because of the in-situ fabric of the cementation and the aging affecting CRR. So in 2004, there was a panel discussion at the Geo Congress where a large group of experts, of maybe the most experts of the world, concluded that no laboratory tests are suitable for liquefaction estimation. Only suitable field tests should be used. Now, most of the liquefaction resistance is done with SBT and CPT, yet with very cautious recommendations. Robertson and Wright said that CRR by CPT is adequate for low-risk projects. For high-risk projects, you should estimate CRR by more than one method. Yud and Idris added that to use 2 or more tests for a more reliable evaluation of CRR. Idris and Boulanger underlined that the allure of relying on a single approach should be avoided. So, for this reason, we decided to use the DMT data for obtaining an additional estimation of CRR. Now, the published research pointed out that KD is quite sensitive to stress history, as I showed you in the recent slide, in the last slides, including aging, pre-stressing, and structure. KD is also correlated with relative density and in-situ state parameters, even though I did not show you this correlation. And these are all factors to be known to have influence on liquefaction resistance. KD is like a cumulative index that takes into account all of these properties and basically gives a performance of the soil increased due to possible cementation, pre-structure, pre-stress, and so on. So this is to explain why CRR was obtained from KD. Also, this experiment further tells us why KD was chosen, because in this experiment published by Yamakowski and Lopresti, they used the Ticino sands and did 5 unload-reload cycles along the K0 line to simulate pre-stressing. And then they did the test before and after this simulated aging. And they saw that KD incremented 20%, whereas the penetration resistance increased only 3%. So KD proved to be very sensitive to pre-stress. So this was just to give basically a basis, a theoretical basis for why the KD parameter was chosen to obtain CRR for its estimation. And as you see, these are the curves that were proposed since 1982, the first very unconservative by Professor Marchetti in 1982. Then you see that the curves started to go narrower and narrower towards the center. And this is the plot of the most recent ones, and the most recent is the red one published by Chiaradonna and Monaco in 2022. So the idea with the SDMT is to obtain 2 independent evaluations of CRR, one from KD using that latest curve I showed you and putting the points and seeing if there are points on the unsafe value, which is on the top left, or on the safe value, safe from liquefaction, on the right bottom. And a similar estimation of CRR can be done with VS, again, using the curves proposed by Andrews and Stokey, which have a small difference according to the fines content. So these are two independent evaluations of CRR. This is an example of an application of these methods. In this case, there was the terrible earthquake of L'Aquila in April 2009, where you can see very well in the picture the cracks of sand, the cracks of the soil with the sand that came out. They had all the data reconstructed, back calculated these parameters with the local university, and they did several SDMT tests. They then plotted both the valuation of the liquefaction CRR versus CSR, and you see that there are some red points between 2 and 6 meters with KD, and from VS there are points between 1 and 2.5. So probably the liquefaction was indicated by both independent methods between 2 and 2.5 meters. So probably it occurred in these layers. Another example was published by Vargas and Cotto in this area in Costa Rica, Pets Vela, where they protected the marina with coffer dams, basically containers with sand that was not compacted. They used the design earthquake values for plotting the CRR, CSR curve. And as you see, there were many, many points indicating potential of liquefaction, all these and all these. And they wrote that just a few weeks after the SDMT execution, the cyclic wave action due to a storm induced liquefaction in these deposits. Of course, we have to see, they should check if the storm was in line with these parameters, but definitely the risk was quite well pointed out with their analysis before the storm. So we are close to the end. Summary and conclusions. We have seen the DMT, SDMT, and Medusa D and SDMT working principle. We have seen the test execution, both onshore and offshore, the data processing, starting from the field readings up to the geotechnical parameters. We have seen the main graphs of the test results and how to read them for geotechnical analysis. Comparisons with geotechnical parameters are obtained in well-documented research test sites performed by high-quality tests and university staff, so that the parameters were well identified with many different instruments. Example of results and case histories and projects, and the main applications for geotechnical design that I wanted to present you in case you had similar ones. So thank you so much for your attention, and I'm available, of course, for questions now or also by email if you have any. And thank you all for attending this presentation.
Thank you so much, Engineer. It was an excellent presentation. We are very pleased having here you. Now we're about to pass to the next question section, which is questions and answers by all your experience. So I'm going to start with the first one, if you don't mind. Or Sandro, if you want to say something to the public. Okay.
Thank you, Shirley. Thank you very much, Ingeniero, for your presentation. We consider that it has been a very interesting topic. I am sure that the audience present managed to enjoy and learn a lot thanks to you. If you agree, mi colega Shirley will begin with the question sections.
Yes, please.
Shirley, las questions.
Engineer, we have the first one. We say, are there recent development for estimating the KO at-rest lateral earth pressure coefficient with the DMT in sandy soils?
Well, in sands, as I did not have the possibility to go into details, I did a presentation elsewhere where I addressed this topic. But with the DMT, currently, now with the Medusa, we are making other measurements and we will research if it's possible to improve. But in sands, K0, you can get a reasonable estimate, but not as reliable as in clays. And the reason is that with the DMT, you can sense the difference, but you have to first fix it. So either you do a local calibration and you know in a point where it is, and then you do the ratio and you can see the increase of K0, but not like in clay, you have a direct formula from K0 to OCR or K0. There are some formula, several, I heard people used it with, even with satisfaction, but Professor Marchetti said he didn't want to put it in the software because it's not worldwide valid. So you must do a local correlation to make this connection.
Thank you, Engineer Marchetti. We go to the next one, which is one of the most important industries in Peru are tailing dam design and construction in copper, silver, and gold mostly. CPTU testing has become widespread in the last decade.
How can the DMT add value in tailing geotechnical tech? Well, today, I would say that 60% of our clients of the DMT are doing the test in tailings dams. Not only for the DMT, also for the seismic, and many seismic CPT are done with our SDMT combined with the CPT. In terms of DMT, we are doing that there are being done several tests with the Medusa, because the Medusa is able to perform additional measurements compared to the DMT, like penetrating continuously like the CPT and measuring the horizontal stress, because the Medusa is able very rapidly to measure A reading. So you can take the A reading fully undrained as you penetrate the soil without stopping. And this is being published in many research papers already in the latest conference of ISC. And we are publishing additional experiments performed in cooperation with NGI. They are being very much requested in many tailings dams in Brazil, Australia, and Canada. I don't know in Peru.
Thank you, Engineer. Yes, it was part of the questions. Now we can pass to this one, which says, as an engineer, what do you think has been your biggest challenge?
Well, the seismic equipment was quite, I suppose you mean in making the instruments or in a project, because it can be a very different answer. I mean, are you talking about a special project that was very difficult to do the tests, or what was the major challenge to construct and make the equipment useful for geotechnics?
In both cases, might be.
Okay, well, the most challenging was definitely when we went to almost the North Pole to combine the DMT, the Medusa DMT, to go down 1,500 meters below water level, below sea level, because the pressures were very high. So we had to design the Medusa and put basically the construct and design and create that instrument you saw, and to make it go at those depths. It was not simple at all, but we did it and are very happy. Concerning the difficulties for making this equipment, we designed the seismic equipment in 2003, but until 4 or 5 years ago, or maybe even 3, we did a lot of improvements that we got on site and by feedback of our users. And this helped us to improve it continuously and to make it now much more simple. So it was a quite extenuating project, because it never ended. You always think that you're finished, and you're not finished. You always can do better. So you try to improve, to put the inclinometers, to put the P waves. So it's always trying to go further with the equipment, with the easiness of usage, and with the interpretation. We cooperated with NGI 1 month in June to do tests with very different test procedures and try to see if we can get additional information on soil mechanics. So we are very, we tend to be in direct contact with research to try to improve the understanding of the soil.
Thank you so much for sharing this experience, engineer. And the last one that we have is this that says, what would you recommend to civil engineering students who wish to specialize in this topic?
Well, I would recommend them to try to understand this test, which maybe is not so common in your country, and especially to distinguish the difference with the CPT, because together the DMT and the CPT are very strong and powerful, because one measures strength, the DMT measures modulus and stress history, and with these three information, you really will understand the soil in depth, instead of having only points of samples and a very low quality results from SPT. And you have to impose yourself to require in projects good data. You cannot do design if you don't have a good geotechnical profile, because you will have to over design, lose a lot of money, and be frustrated because you're not doing your job well. So when you will do design, you have to tell your client that he has to spend money to know the soil. You do a good design, and he will be happy to save money in the project because you do a better job and you're all happy. That's what I think. Sorry for being so tight, but it's really an important point. You know, in the world, SPT is still the most common test when you have CPT, which is much better, and the DMT, which we believe even superior. And you cannot stay with a test that was born more than 100 years and that consists of just hammering a point below the ground.
Thank you so much, engineer, for your advices and your recommends. And thank you very much for this once again, for your excellent presentation. It was an honor to come with your presence today. We all, as all the members of GeoUPC student chapter and all we are present, we are grateful for you agreeing to share your valuable experience and teaching that with us. On the other hand, we want to leave you with the invitation to participate in future conferences with us. And we thank you again for your brilliant participation today, supporting us in this Congress. We wish you the best success and many blessings. So if you would like to share some goodbye words, we are all ears to hear you.
Sorry, if you would like
to share some goodbye words to the audience.
Yes. I would like to thank you all for inviting me to give this presentation, and in particular to Mr. Bonilla, Suarez, and Roman for all their organization, starting from the beginning till today that we completed this presentation. A big thanks to all of you in Peru. I have been in your country. I would like to come back in some future, so it would be nice maybe in the future to have a real conference in your place. And good luck for your career, and remember what I said before about the quality of the data. Okay? Ciao.
Thank you so much, engineer.
Bye. Ciao.
No,
Thanks.
Bye.